These are the 5.2 part 1 video notes, and we're going to start looking at one-to-one and inverse functions. We're going to cover everything about one-to-one functions today, and then we'll start breaking down inverse functions. We're going to start today. We're going to look more tomorrow. So one-to-one function definition. A function is a one-to-one function if any two different inputs in the domain correspond to two different outputs in the range. That is, if x1 and x2 are different inputs of a function f, then f of x1 can't be equal to f of x2. Super mathy definition. What does this mean? Let's break it down into plain English. So we learned with functions, if I had a function that looked like this, if I had two inputs and those inputs were the same, if I input something 2 and then I got an output of 3, and then I input 2 again and I got an output of 5, it's not a function. I can't have the same input with different outputs. That's not okay. But what we did learn was that I could have multiple different inputs and all of those inputs could have the exact same output. And we learned that that was okay for functions. And it is, and it still is okay for functions, but what it's not is this is no longer a one-to-one function. Once you repeat your output, you no longer have a one-to-one function. And it's not anything, we're just adding a new level of degree of exactness. It's like saying all squares are rectangles, but not all rectangles are squares. All one-to-one functions are functions, but not all functions are one-to-one. And that's okay. So we just have to add in that extra degree of what is a function and what is a one-to-one function. Where are they specific, where are they not specific? So we've got our one-to-one functions example here. If we look at figure 6, this is one-to-one. Every input has an output, and exactly one output. And here's a good way to test one-to-one, is if I ask, if I give you an output and I say, which state has a population of 6.2 million? You can tell me it's Indiana. It's exactly Indiana. There's no ambiguity there. You know that the only state with a population of 6.2 million listed here is Indiana. If I ask you which state has a population of 8.3 million, you can tell me it's North Carolina. Only state on this list with a population of 8.3 million. We know this to be a fact. It does not change. Cool. So that means it's one-to-one. When I ask about the output, when I ask which input relates to this output, you can give me one answer and only one answer. Figure 7 is not one-to-one. And it's not one-to-one because if I ask, which animal has a life expectancy of 10 years? You could say duck, pig, or lion. So I don't know which one it is. Like, for example, I come up to you and I say, I'm going to give you a gift. And this gift is an animal that has a life expectancy of 10 years. And you're looking at this chart and you're saying, whoa, 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 whoa. I don't want a lion. And I'm saying, can you at least tell me it's not a lion? And I'm just saying the only information I have here, I went onto a website and it said it was going to sell me an animal with life expectancy of 10 years, and I'm going to give you that as a gift. I've got no information here outside of its life expectancy is 10 years. Suddenly somebody who isn't ready for a lion pet might be sweating and saying, I really don't want a lion. This is why it's not one-to-one, is because when I'm asking about the specific output, you can't give me a definite answer. Now, it still is a function. 100% it's still a function because if I ask about the input, if I say, what is the life expectancy of a lion, you can give that to me exactly. You can say, life expectancy 10 years. What is the life expectancy of a dog? Exactly 11 years. The inputs don't change. That still is a function. It's just that it's not one-to-one because if I ask about the outputs, then you're starting to give me different responses. So that leads us to this idea, the horizontal line test. We did the vertical line test for just straight up functions. If the x value repeated itself, it wasn't a function, which is not okay. We don't want that to happen. Now, we never concerned ourselves with the y value repeating itself. If the y value repeats itself, that was always okay with functions. Well, now we're going to do our next level. We've done the vertical line test. It's a function. Now we're going to do the horizontal line test to see if it's a one-to-one function. So if the y value repeats itself, it's not there. That's kind of our test for one-to-one functions on a graph. We can see with A, we draw a horizontal line right away. Our y value repeats itself. It's not okay. It's not a one-to-one function. It still is a function. It's not one-to-one though. B, every horizontal line intersects the graph exactly once. So we call it a one-to-one function. All right, cool. That works out. And we can say definitively now that all even degree polynomials are not one-to-one. Even degree polynomials may or may not be one-to-one. It really depends on what's happening with those even degree polynomials. Some of them do have those increasing to decreasing periods, but we can say definitively all even degree polynomials will not be one-to-one. So inverse function. Suppose that f is a one-to-one function, then to each x in the domain of f there's exactly one y in the range because f is a function, and to each y in the range of f there's exactly one x in the domain because f is one-to-one. The correspondence from the range of f back to the domain is called the inverse function of f. Now, technically speaking, if a function is not one-to-one, it does not have an inverse function. Now, we will look at trying to write inverse functions for functions that aren't one-to-one. We're going to have to put restrictions on it, though. And the idea of like a true inverse function is that we can just say the inverse exists regardless of restrictions. We don't have to change domains. We don't have to change ranges. We don't have to write any crazy rules. We just have a straight up, here's your function, here's your inverse function written. They're based on one-to-one function ideas. Again, we will look at writing a function that is not a one-to-one function, writing its inverse and then putting in restrictions. But technically speaking, if it's not one-to-one, we don't have an inverse function. So inverse functions by mapping diagram. Again, this is just what I verbally said up top of if I have my input of states and my output of population, my inverse function means that my input is population as my output is states. I'm asking in the reverse order. I'm saying, I'm basically changing the function machine. If I had a function machine where I'm going online and there's this website that you can type in a state and it spits out a population, cool. Then you hit the inverse button, it changes its algorithm, and then you can type in a population, it tells you the state. This is what the inverse function is. It's basically going back and forth. Oh, another really good example that just popped in my head. Inverse functions exist on Google Translate. If you go to Google Translate, you can go English to French. Well, then you can hit the flip and it can take you French to English. That's an inverse function. The original function was you input an English word and outputs a French word. The inverse function is you put in a French word and it outputs an English word. Same thing. If I input rat in the English side, I'm going to get raton on the French side. If I put raton in the French side, I'm going to get rat on the English side. The input and output doesn't change. It's just a matter of where it was put in. So finding an inverse by a set of ordered pairs, make sure on your notes you change this. I did not make this first 27 negative. I had to add that in. I did not make that first 1 there, -1. Right now, the way it's written in your notes, it's not 1-to-1. By putting those two negatives in, you now have a 1-to-1 function. So if I want to find the inverse function here of this set of ordered pairs, first of all, I'm going to denote it like this. I say f to the -1 power of x. That denotes an inverse function. So I'm saying the inverse function of x. And all I do is flip my x and y values here. I'm flipping my inputs and my outputs. So you can see all I'm doing here is changing my y values. I'm making what were my original y values my x values. I'm making what my original x values are my y values. I can look at this inverse function. I can see that my inputs don't change themselves, especially once I change those two values to the negatives they were supposed to be. And I can see that my function here, it's a function, everything's flipped. This is what my inverse function is. I'm just changing what my inputs and outputs are. So I've got this visual here. So I've got the domain of my function, which are the inputs, and the domain of my function, which are my inputs, are going to be equal to my outputs for my inverse function. Because when I plug something into my function, and then I put it through the function machine, however you want to think about that, and I get over here, I get to my range of my function or my outputs. Well, my inverse function machine, what I did was I put the inputs into those inverse functions and got it to the range, and those are my outputs. The outputs of my inverse function are equal to the inputs of my original function, just like the outputs of my original function are equal to the inputs of my inverse function. They're equal values every single time. So what that means is if I put an input into my function and then I get that output and I put that output in my inverse function, I just end up with x. Just like if I put an input into my into my inverse function. I get an output from that, and then I put that output into my original function. I'm just going to end up with x. So this leads back to what we learned in 5.1 of those equal composite functions. If I have equal composite functions, then I can say definitively I have an inverse function. So looking at here, verify that the inverse of g of x, so x cubed is the inverse function of, or the cube root of x is the inverse function of x. So what I need to do here is I need to find the function that is composed of g as composed by the inverse of g, and I need to find the inverse of g as composed by the function g. So if I plug in the inverse function that I'm being told here into my function, these cross out and I'm left with x. If I plug my function into what I'm being told is my inverse function, these cross out and I'm left with x. So because g of x, g as composed by the inverse of g of x, and the inverse of g of x as composed by g of x are both equal to x, I can say they are inverses. Because those composite functions are equal, they are inverse functions. And I can do this again. So we're going to verify this. We're going to figure out my function composition with my function composed of the inverse function, or what I'm being told is the inverse function. We're going to check to see if it is the inverse function. And the composition of the inverse function composed of the function. So I've got 2 times 1/2 x minus 3 plus 3. Those cross out. X minus 3 plus 3. Those cross out. This is x. I've got my inverse. So I've got 1/2 times 2x plus 3 minus 3. These will cross out. 1/2 of 2x. And then again, f as composed by the inverse of x and the inverse of x as composed by the function of x are both equal to x. So they are inverse. And that's how we confirm if something is an inverse function. So that is all we have for today. Tomorrow we will actually look at finding the inverse function, but once you find the inverse function, you might want to check yourself. So you can go through this process, and I will touch on that in our next set of notes. So once we start learning how to take the inverse function, we will learn how to check to see if we actually have the inverse function. If you have any questions or concerns on the homework, please reach out as soon as possible, and have a great night.